So we're going to look at descriptive statistics, and we're going to look at how to come up with grouped data and also using the empirical rule. But before we do that, we'll just do a quick recap of what we discussed today earlier on. So we made mention to say we need to distinguish between these two polygons. There's a polygon which we call a bar chart. A bar chart is used for discrete data, A, B, C. Town A, town B, town C. All right. Continuous data is illustrated by what is called a histogram. So you need to know which data is continuous and which data is discontinuous. So in this case here, we're asked to elaborate on the daily demand, where we're given the demand 0, 1, and 4. So we're asked to come up with what is called a frequency distribution table. So here we had to identify the variable X or the daily demand. So our daily demand here, we had numbers starting from 0, 1, 2, 3, and 4. So if you count how many zeros we have, there are 4. How many ones we have? There are 2. How many 2s we have? There are 7. How many 3s we have? There are 4. How many 4s we have? There are 3. So this is how we came up with a frequency distribution table. And to come up with what is called the cumulative frequency, we add on. So the cumulative frequency is simply computed by adding on. We start with a 4 there. 4 plus 2, 6. 6 plus 7, 13. 13 plus 4, 17. 17 plus 3, 20. This 20 is the same total that we have that side. So this is how we come up with the frequency distribution table. Now, to come up with a relative frequency table, we simply total up 4 divided by 20, 0.2. 2 divided by 20, 0.1. 7 divided by 20, 0.35. 4 divided by 20, 0.2. And 3 divided by 20, 0.15. So whenever we're talking about relative, it is each individual element over the sum total. Similarly, if we're being asked to find the relative cumulative frequency table, relative cumulative frequency would actually be asked to divide 4 out of 20, 6 out of 20, 13 out of 20, 17 out of 20, and 20 out of 20. So this is how we find our relative frequency table. So relative, alternatively, you can bring the 0.2 here. We add the 0.1, get 0.3. We add 0.35, we get 0.65. We add 0.65, 0.85, and we add to get the last number, which is 1.0. So this is how we come up with the relative cumulative frequency. Now, this is dealing with daily demand. So we could be sometimes be given information as follows, where we are asked in a data set that has been given. We have been asked to do what? To develop a frequency distribution table. Now notice here, we have information that is kind of diverse. There are a lot of possible outcomes here. The previous example we're looking at now is the range, the variety, the degree of dispersion. The lowest number here is 0, and we have the highest number here, which is 14. So it will take the whole day to do. So we need to come up with what is called a class width. Class width is simply, we find the range, and we divide it by the number of classes that we want, k. So this is what we call the class width. So the highest number here is what, 14? The lowest number is 0. And if we want to have how many classes? 5 classes, we can divide this by 5. So 14 minus 0 is 14. Divided by 5 is 2.8. So roughly, we're looking at a class width of what? 3. So you can now start regrouping them. So you say 0 to 2, these are 3 numbers, 0, 1, and 2. Then 3, 4, 5, these are 3 numbers. 6, 7, 8, 3 numbers. 9, 10, 11, 3 numbers. 12, 13, 14, 3 numbers. So this is our class width. So each of the classes includes 3 values. So it's inclusive of them. So this is computed by finding the range. The range, we're talking about highest number minus the smallest number divided by our k. All together, so k stands for the number of classes that you wish to have. So if you want to have, for instance, 5 classes, you divide 14 minus 0 divided by 5, which is 2.8, so 3, the class width. So now we identify which numbers lie between 0 and 2. When we go here, there is 1. Start from here. We have 1 itself, 0. So we have 2 numbers here, 1, 2. We're talking about 0 to 2. 1, 2, 3, 4, 5. Right. So 1, 2, 3, 4, 5, 6. So these are 6 numbers. That's the frequency we're getting here. Then 3 to 5, we check them out again. We discover that they are 11. 6 to 8, 7. 9 to 11, 4. 12 to 14, there are 2. So in coming up with the class width, you need to be very careful that they don't overlap. You cannot choose 0 to 3, then 3 to 5, then 5 to 8, unless in your mind you're not including the last number. So this is the only reason why you could safely don't overlap them. So 0 to 2, 3 to 5, 6 to 8, 9 to 11, 12 to 14. Then when you check there, you're having this frequency table. So thereafter, you can come up with a relative frequency by dividing each of the entries divided by the total number. So 6 divided by 30, 11 divided by 30, 7 divided by 30, 4 divided by 30, 2 divided by 30. So these are the figures that are called the relative frequency points. Similarly, to find the cumulative relative frequency point, we add on. We start with 0.2, we add to 0.36, we get 0.567. We add to 0.23, we get 0.8. We add to 0.133, we get 0.9533. we add to this one. The last number must always be 1. That is for the case of our cumulative frequency. That is in that case. Are we following so far?
Yes.
All right. So we follow now in coming up with what we call the bar chart and histogram. So when you're given information, for instance, we're given a grade like A, B, C, want to see the distribution of the grades in a class of statistics. So 9 got an A, 12 got a B. So now the kind of information that we have here, even if we know that a histogram is supposed to be continuous, you need to know that this information here represents discrete data. You cannot have an A and a B at the same time. They don't touch. They're distinctive. So this is a histogram, quite all right. But you put points like this here to just show that there's a gap in between, which is because the information we're looking at is what? Discrete. So you cannot, in the countable values, those that got A at 9, those that got B at 12, those that got a C at 6. So this is what we call our histogram. So you need to also know specifically when to use the spaces. The same can be done by given information of employees who are commuting. These are 50 employees in a company. So 0 and under 5, 4 and under 8, 8 and under 12. So you're being asked to come up with a what? A histogram. So for this one here, we're going to put 0, 4, 8, 12 up to 24. So this one has no gaps in between because the data is continuous. So continuous data, we always assume that any value in an interval, a person can drive any distance between 0 and 24 miles. So we can't leave any gaps. So we are talking about commuters here. So in here, there are no gaps that we are leaving out. So you need to know when not to leave gaps. The data that we have here typifies and groups data. Like I said, the first thing is to find our class width. So you can choose the number of classes that you wish to have. So we, in this case, have 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 4 by 10, that is about 40. Our n is 40. Okay. So there's a rule that we use sometimes to help you predict a good number of the classes that you need to have. So we use this formula: n number to the power k must be equal to or less than our n. So in this case, we need to find a number that we can power 2 to. The number must not be more than 40. All right. So we can try 2 to the power 3 is 8. So that is 22. It must be close. 2 to the power 4 is 16, still low. 2 to the power 5 is 32, slightly low. About 2 to the power 6. So 2 to the power 6 is kind of close to 40. It's giving us, it should be slightly greater, the first number that exceeds our n. So 2 to the power 6 will give you 64. So 64 is the first number that exceeds 40. So our base number of our n is 6. I repeat, this is very important. It guides statisticians. So if you have a sample size of, let's say, 64, they'll ask you what is the most appropriate number of classes you should have. So we said 2 to the power k must be equal to or greater than what? N. So what number can we power to get 64? So we're power 2 to power 5 is 32. 2 to the power 6 is exactly 64. So you need to have 64 as number of classes that is appropriate for this kind of data. But needless to say, even if there was what? 50 there, 6 will still be appropriate because it is the first number that exceeds what? Our n, because we put a 5 there with 32, which is less than 50. So this is what we use in this case. So we need to, if we had 100, for instance, sample size is 100. So you try n to the power k, which number will be first exceeding 100. So if we put a 6, already we know that is what? 64. If we put a 7, we're going to get 128. 128 is appropriate for 100 data sets because it's a first value that exceeds 100. I hope you're following. So in our case here, our sample size is what? 40. So what number do we power this one to? We get the number that first exceeds 40. So 2 to the power 6 is what? 64. So 6 is most appropriate. That's step 1. Step 2, you find the range over the k. The range is simply the difference between the highest number and the smallest number. So when you identify here, highest value in this case will be 318. And the smallest value in this case is 265. So you subtract the highest minus the smallest, then you divide by 6. So 6 into the difference, which is the range there, we're going to get our nearest whole 10th number, which could be 10 or even 9, the countable numbers. So in this case, since we have 40, 10 is appropriate, which can go into there appropriately. So meaning we're going to look at a range of values 260, because the lowest value here is what? 265. So we can say 260 to 270, 270 to 280, 280 to 290, 290 to 300, 300 to 310, 310 to 320. The highest number here, which is what? 318, is still capped within this this range. Then you now start looking for the values that will lie between 260 and under 270. There are 2. 270 to 280, there are 2. 280 to 290, there are 10. 290 to 305, 300 to 310, 12. 310 to 320, there are 9. So the total comes about the 40. Now this kind of information has to be typified in a histogram. So 260 to 270, we have 2, 270 to 280, 2, 280 to 290, we have 10, 290 to 300, we have 5, 12, and 9 respectively. Now, why are there no gaps there? Because we're considering the type of data, which is what? Mileage. And mileage, what kind of data is it? It is continuous. So you don't include the gaps. So earlier on today, we discussed the 2 types of data to say there is continuous under quantitative, and we also have what? Discrete data under quantitative. Are we together so far?
Yes.
Okay, so now we proceed to our lesson for this evening, where we're going to learn our type of measures of central tendency. We have what we call ungrouped data. What is ungrouped data? We talked about ungrouped data as data that is what? That is not put into groups or clusters. So we have 2, we have 4, we have 20, we have 3, we have 4, we have 5, we have 2. So this data that we have there is ungrouped. So the first thing we need to do is to rearrange the data. So this data can be rearranged in ascending order. So what is our smallest value there?
2,
Then
3,
2 again, then 3,
3, 4, 4, 5, and 20.
20. 1, 2, 3, 4, 5, 6, 7. So our n is what? 7. Meaning our n plus 1 is what? 8.
Mm.
All right. So
Okay.
square each of these ones here. So these are values of x. Maybe we can square this individually. So this is 4. This is 4. This is 9. 16. 16. This is 25. And this is 400. Right? So when we total up this one, it's called the summation of x squared. When you total these ones here, they're called summation of what? X. So let's try to add up and see the values we're going to get. I hope you have a calculator.
I'm going to get it.
All right. So make sure you always come with a calculator. So we're going to get a 40 here. We're going to get a 424 here. And our n was 7. So
Sorry to take you back. So if our n is still 7, why did we say n plus 1 equals 8?
when you add 1 to 7, it's 8. So this is important for what I'm about to explain. So we're going to look at what are called measures of central tendency and dispersion. So let's start with the easy things, the range. The range is the difference between the highest number and the smallest number. So what is the highest number of x and the smallest number of x?
20
20
and 2,
minus 2 is 18.
18.
So that is what we call the range. Okay.
Okay.
The mode is the number that appears the most. What number appears the most there?
So we have 2 and 4.
2 and 4. Excellent. So this is a bimodal frequency. We have 2 modes. All right. Then the median is the middle, half of n plus 1. Now this is where your n plus 1 is important. N plus 1 was
Okay.
8, right?
Yes.
Half of 8 is what?
4.
The fourth number. What's the fourth number here?
It's 4.
2, 3, 4. Coincidentally, it is 4. So our median is denoted by the letter Q2, which is the second quartile. So our median In this case, what? So we also have what we call Q1, which is a lower quartile. Q1 is
Okay.
lower quartile, given by a quarter of n plus 1. What is our n plus 1?
8.
What is the quarter of 8? Second number, 2, right?
Yes, sorry, husband.
So coincidentally also, our second quarter is what? The second position,
2.
2. Go to our third quarter, which is 3 quarters of n plus 1. Our n plus 1 is what? 8. So 3
Mm-hmm.
8 is what? 16.
Sorry, do that one. Don't have it. Okay. 6.
So Q3 is for the upper quartile. All right. So
Okay.
the sixth position in this case is what?
5.
5. So meaning our Q3 is 5. Okay. All right, so let's do a quick recap. The first thing we did in this case was rearrange. Rearranging is important because of the quartiles. If you don't rearrange, you get the quartiles wrong. The second position would have been a 4, which is wrong. The second third would have been a 3, which would have been wrong. Maybe you'd have been like to get a 5, but you need to rearrange. Is that clear? After rearranging, we found our range. What did you say the range was?
Yeah, sorry.
The range is the difference between the highest number and the smallest number. All right. So in this case, range was difference between what? 20 minus 2, we found 18. Is that clear?
Yes.
The mode was the most appearing frequency. We had numbers like 2 and 4.
And 4.
So this is what we call the mode. We went to the quartiles. We started with the lower quartile. The lower quartile is a quarter of n plus 1. So this is a quarter of 8, which is the second position. We got a 2. The upper quartile is 3 quarters of n plus 1. 3 quarters of 8 is the sixth position, which we got as 5. And the median is the second quarter, which is half of 4, 8, which is 4, which we found as what? As 4. Now this one, we wanted to come up with what we call a box whisker plot. Box whisker plot has 5 key elements: the smallest value of x and the highest value of x. And we have the Q1, Q2, and Q3. So the smallest value of x was what? 2, and the highest was what? 20. So you put your 2 there and your 20 there. The lower quartile was a 2, then median was 4, and upper quartile 5. So 2, 4, 5. We have a 2, 4, and 5. So coincidentally, this 2 is actually even the at the lower quartile here. So I hope you understand what I'm doing here. I'm just trying to scale that the lower quartile is the same as the minimum value of x. It's at the same point because we have a 2 as a lower quartile, and the smallest number was what? A 2 as well. You get it, right?
Yes.
And there. All right. Then the interquartile range was the difference between the highest quartile and the lowest quartile. So 5 minus 2 is 3. The interquartile range is the difference between the highest quartile. We use IQR. IQR is Q3 minus what? 1. So the upper quartile was 5, the lower quartile was 2. So we get a 3. So that is a 3 there. So far we together?
Yes, I think I can run through. So you're saying Q1 should always be the same line with X mean, is it?
It's just coincidentally in this data set, it's not always.
Okay. Okay.
It's not always.
All right. Got it.
It's one of the rare moments. All right, so after we're done with this, we want to identify an outlier. An outlier is simply the odd one out. What is coming out of what context? So to these three, you multiply by a standard value, which is the correction term, 1.5. Apply 1.5 to this, we're going to get 4.5. Now this 4.5 is the standard value. We add it to this upper quartile and we subtract it to this lower quartile. So if we add a 4.5 there, we're going to get a 9.5. We're going to subtract a 4.5 from there, we're going to get a negative 2.5. These are the critical values that will identify the numbers that will lie outside these ranges. So in this case, our 2 is captured within here. So this is not an outlier. Then the 20 is out of range, is out of this 9.5. So we can say 20 is an outlier. So this carries about 5 marks. Let me repeat. If you had numbers like 2, 5, 8, 8, and 10, okay? So in this case, what is our n? 1, 2, 3, 4, 5. Our n is 5, right?
Yes.
So what is our mode in this case?
2, 3, 8.
8, correct. Find the lower quartile.
The lower quartile. Let me see. Are we going to see? It will be
Quarter
1 over 4
n plus 1.
plus.
So
So it will be 6 in there,
mhm.
which will be, okay, let me get that one there. So 2, 4, to be 1 point what? It's going to be a decimal, isn't it? A minute, sorry. This thing is not getting.
We get
So
6
I'm back.
divided by 4 is 1.5. Okay. The nearest, this is the second number. This is our second number here.
Okay, so our second number is 5.
All right. The number is 5. So this is our Q1. Okay, then our Q2.
So that's half.
We put that, oh, Q2 is half, yes.
Half open bracket 6, n plus 1, 6.
Half n plus 1 to 6, all right? Of 6,
3,
the third number. The third number.
8.
Right. Then our Q3.
So our Q3 will be 1 over 3.
Hmm.
Yeah, so 1 over 3, open brackets n plus 1, which is a 6.
Mm-hmm.
Okay, oh, sorry, it's actually 3 over 4. I was wrong. Eh? So 3, allow me to do that one. 3 over 4. It should be 4.5, is it? No. So I need a calculator. Sorry, help me with that one. 3 over 4.
Divided by 4. Yeah, 4.5. So 1, 2, 3, 4. 1, 2, 3, 4. Okay.
So if it's 4.5, then I do it.
Okay. So ideally, whenever I have a 0.5, it means that number, and the second number you get the average. So 4.5 means what?
So it means we add 8 plus 10, which is 18, divide by 2,
Okay.
9.
Yes. It's 9. It's the same thing we're supposed to also do here. Since we found 1.5, so this plus that
Okay, 7.
divided by 2, which is 3.5.
So we will take it to 4.
So this is 7 plus. No, here you get the actual values.
Okay.
Here 8. And here we have 9. All right, so just trying to emphasize the concept that we're learning there. So the box Fisker plot, the lowest value of x will be what? 2. The highest value of x will be what? 10.
10.
The lower quarter was what? 3.5.
3.5.
The median was what?
8,
And the upper quarter was what?
9.
And the quarter range will be what? 9.
So interquartile.
The highest quarter minus the lowest quarter.
Okay.
9 minus
So that's 3.5. So okay.
5.
5.5.
Then you multiply the 5.5 times 1.5. It's the correction term. Get 8.
Okay. 8.25.
Good. So this one, we add it to this value. This one we subtract from this value. So when we add the 8.25 plus 9, we get 17 point what? 25.
25.
Meaning the 10 has qualified, it's not an outlier, it's inside. And we also subtract 3.5 from there, 8.5. We're going to get
11.75.
11 point what? We subtract this one,
7. Oh, we're subtracting that one. Okay.
3.5 minus 8.25.
4.75.
4.75. So meaning the 2 is inside as well. So meaning we don't have an outlier.
Okay.
So the concept behind this box Fisker plot is there to help you identify whether we have an outlier, an odd one out. It's also very important because you'll be able to understand really what data set is odd. For instance, when you're dealing with audit queries, dealing with transportation to various destinations, and within a locality, you know the average expense is 1,000, 1, 2, and suddenly you have a 4,000 within the same radius, then just know it's an outlier. It's an audit query. Even if you don't know, you query because an outlier. All right.
Okay.
Important to identify in extreme situations. Why is it that in a child family of 5, there's this one who's peculiar? Maybe she's oddly disciplined. You could perhaps think she's adopted, or oddly intelligent. And you'd question to say, are you really from the same parent? So outliers are very visible in the sense that you see something distinctive about them. All right, so now we go to another set of parameter, which we call measures of central tendency. Now, we want to learn how to come up with the mean, standard deviation, and the variance. So you're given values like 2, 4, 6, 8. All right, our n here is what? 4.
4.
We square these ones here. This is what? 4 and 64. I mean, summation of x squared, because we are squaring these.
Okay. Mm-hmm. One, 120? Am I correct? No.
Yes. So to find the mean, symbol for the mean is x bar. This is simply found by this formula, summation of x over n. And here we have 20, and our n is 4. So our
5.
is going to be the average, which is 5. We also have what we call the variance for a sample, which is denoted by the letter s squared. So this one is given by this formula, which you need to master. So follow these formula very well. Our n is what? 4. Everything over 4 minus 1.
Mm.
Let just follow through this. So 120 minus 400 over 4, which is 100, divided by 4 minus 1, which is 3.
Mm.
So this is 20 over 3. Our variance, therefore, will be 6.67 or 20 over 3. Okay.
Following.
All right. So that is what we call our variance. So the standard deviation is simply when we square root our variance. We don't have, just square root this. So 6.67 square root. That answer will give you 2.58. Preferably leave it to 3 decimal places.
Okay.
And finally, you'll be asked to find the coefficient of variation, which is simply given by the standard deviation over the mean times 100. So 1582. The mean we found as what?
The mean we found 5.
5. Then times 100. Okay. We get
Okay.
1.48.
— 51.
So this is how we deal with what we call ungrouped data.
Okay.
First thing you need to practice for such a course, it is all about understanding
Can you kindly go to the variance a bit? I don't know why my number seems to be different from yours. When we square
we start with
the
120,
summation of x squared, we got 400, isn't it?
400
Okay, I think it's there.
divided by 4.
Well, I'm not too sure where I'm missing it. So we said summation squared, that's the 120 which we got from the top. Okay, so we squared the 120 as well.
No, 120, leave it as it is. 120, leave it. So 20 squared,
Because it was already squared.
yes, it's already squared.
Okay. Then that was 20 squared, which is a 400.
Mhm.
But I'm wondering where you've gotten the 100 on the other side.
So 400 divided by 4 is 100. So this one gives you 100.
Okay. Okay, I forgot the n at the bottom there.
Okay, this n.
Okay,
Right.
thank you.
Okay, so far, so good.
Yes, so far so good. Thank you.
All right. So I'll end at where we're going to convert the grouped and group data to group data. So our next lesson will be in understanding how to convert and interpret ungrouped data. For instance, you're given 0.01, 03, 03, 14, 15, 16, 16, 20, 22, 24, 28, 9, 30, 31, 32, and 42. So you'll be asked to draw a stem and leaf diagram. So deliberately, information is already what? In ascending order. We have what we call the stem, and we have what we call the leaf. The smallest numbers are starting with the zeros. We have ones, twos, threes, and fours. So we have 0, 1. So we put 0, 1. We'll put a 1 there. 0, 3 is already common. Another 0, 3, 0 is common. So we're done with the zeros. On the ones, 1, 4, 1, 5, 1, 6, another 1, 6. On the 20s, 2, 0, what? 2, 2,
2, 2, 2, 4,
8,
8,
2, 9.
9,
The threes, 3, 0,
0,
1.
1, 2,
40s, we have what?
2.
Excellent. So this is what we call a stem and leaf diagram. So we have 1, 2, 3, 4, 1, 2, 3, 4. So n is 16, right?
Mhm.
So we're able to tell here what our mode is. Our mode, the numbers that appear the most, double 3, double 4. So this is 0, 3, and this is 16. So we have 3 and 16. The range, since it's already in order. We have 42 minus what?
0, 1.
Is 41. Okay, the median is what? Half of n plus 1. N plus 1, 17. Half of 17 is what? 8.5. 8.5 means the 8th number and the what? 9th number, right? By 2. So let's count 1, 2, 3, 4, 5, 6, 7, 8, 9. So which numbers are these? 20 and what?
22.
Divided by 2. So meaning our median is what? 1.
1, 2.
All right.
Okay.
And we go to the lower quartile, the quarter of what? Quarter of 17.
Okay.
So 17 divided by
4.5.
4.25. Remember, in short, 1, 2, 3, 4, 5. What number is this?
Where are we? Okay, 15.
In Q3 is 3/4 of 7.
Right, I'm getting a bit slower.
Right.
Mm-hmm.
So a quarter of 17 is 4.25. You get the nearest figure, 5th number.
Yeah.
It was 0.75. So now, at this point, I need to emphasize one thing. So I'm telling your understanding based on your lecturer, what he,
Okay.
other books, well, they're different. Okay, so he has a tendency of following the whole number, unless it's 0.5, where he's going to pick any of the two together. So if it was another lecturer, they would pick a 4 there because the nearest whole number is 4. But here there's 25 or 4.75, he'll pick the next whole number.
Okay.
Okay, let's mention that. So if you have upper part, the 3/4 of what? N plus 1, 3/4 of 17, 0.75 17, which is 12.75. How are we going to pick?
I'm getting 0.0 something.
3 times 17 divided by 4. Hello, can you hear me?
Yes, so it will be 30.
Yeah,
The
so
13th number.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yes, it'll be 30, correct. The following. So the 30th, the 17th number is 30. So meaning interquartile range will be now the difference between the highest quartile minus the lowest quartile. All right. Then whatever follows, you will
30 minus what? 15?
yes.
Okay. Sorry, that's 15.
15. Okay.
Mm.
So I don't want to really go into finishing it up as much, but I will
So, and just right there. So if I got the interquartile range to get the correctional something, you just multiply by 1.5?
yes, by 1.5, that's all.
Okay.
Yes. Then you add it to the upper quartile and subtract the lower quartile to identify.
And the lower quartile. Okay.
Yeah. All right. So we end here for now.